Hello, welcome again. We are covering the subject thermodynamics for civil services mains, IFS and various gate exams. And now we are covering the chapter entropy. In this, the next topic is to find out the entropy change of constant volume heating. Suppose we have a gas of mass 1 kg and it is heated at constant volume, such as entropy changes from S1 to S2 and temperature changes from T1 to P1 to P2. So we have to find out the entropy change. So heat supplied is CV T2 minus Tv. Okay, because it is constant volume process, so heat supplied is Q is CV T2 minus Tv, or in differential form it is dQ is equal to CV dt. So if we divide both sides by T, then it will be dQ by T, and on the right hand side it will be CV dt by T. So dq by t, as it is reversible process, so dq by t can be taken as 0 because it is reversible process. As we have drawn by a solid line, so it indicates reversible process. So dq by t is a 0 and it is equal to cv dt by t. Now we integrate it within the limit, then the entropy change will be here S2 minus S1 CV ln T2 by T1. Okay. So next process is heating of gas at constant pressure. So here this is the process, and again the gas is heated. Gas mass is 1 kg and it is heated at constant pressure, and so temperature changes from T1 to entropy changes from S1 to S2. So this is your constant pressure heating, and this is your constant volume heating. Slope is different, okay. And end condition for constant pressure heating are this, and initial condition are this. So this is S2 and the T2, this is S1 and T1. Okay. So again in this the heat supplied is CpT2 minus T1. In differential form it is dq Cp dt. Dividing both sides by T, it will be dq by T, and it will be equal to Cp dt by T, or dq by T is your ds for reversible process, so ds is equal to Cp dt by T. So if we integrate it both sides, given limit S2 to S1 and T2 to T1, it will be S2 minus S1 is equal to Cp ln T2 by T1. Now consider another process, that is your isothermal process. So in isothermal process, if you want to calculate entropy change, then we consider isothermal expansion. Suppose we are adding heat, one is your initial condition and two is your final condition. So at initial condition, entropy is S1, temperature is T1, and temperature is constant, so T1 is equal to T2. So at final condition, the entropy is S2. Okay. So in isothermal process, for an ideal gas, there is no change in entropy. So it means Q is equal to W, and Q is TdS. Limits are S1 to S2 or TS2 minus S2. This is equation number 1. And work done, reversible work done is PdV. Final volume is V2, initial volume is V1, and P1 V1 is equal to PV. So P1 V1, P will be equal to P1 V1 by V. So here it is equal. So we integrate it, it will be P1 V1 ln V2 by V1, or RT1 ln V2 by V1. This is equation number 2. From 1 and 2, we have S2 minus S1 is equal to R ln V2 by V1. Because because T1 is equal to T, so we can write this here as P1 V1 as RT1, okay. And this is T also here, so this T and T1 will cancel out, so S2 minus S1 will be here R ln V2 by V1. So this is your entropy change in isothermal process. Next process is adiabatic process, or we can say reversible adiabatic process. In reversible adiabatic process, we already studied that is an isentropy process because dq is 0. So it means dq by t is also 0. So ds is 0. So there is no entropy change. It is equal to this vertical line on ts value.